Welcome to part 5 of Writing Better Code with Reactor 3. In part 4, we introduce the mapping operators. In this screencast, we'll explore the reduce, scan, and collect operators. Let's start with the reduce operator. While mapping operators transform each data element into one or more values, reduce operators combine a data sequence into a single result. To demonstrate this, we'll create the test method and set up code to generate a flux and to print the before and after values. The reduce operator takes a by function as parameter. Our flux is of type integer, so the required by function is one that takes two integer inputs and returns an integer output. Here we've provided a function that returns the sum of the integers input. For clarity, let's change the names of the variables to reflect the intent. In the reduce operator, this produces the sum of all the data elements in the sequence. Let's change the by function, this time to something that gives us the multiplication of the two inputs. This produces the product of all the data elements in the sequence. Note that we do not need to assign the resulting value. The by function needs only to return the new value. The reduce operator can optionally accept an initial value as parameter. Without this initial value parameter, the first data element is used as the starting value. Let's try another variation by replacing the multiplication with division. To get a more meaningful result, we'll change the flux type from integer to double by multiplying each element by 1.0. We also need to change the initial value of the reduce operator to the same type to make this code work. Let's look at the scan operator next. The scan operator works the same as the reduce operator, except that it also emits all intermediate result downstream. If an initial value is provided to the scan operator, the initial value is emitted downstream as the first element of the data sequence even before the first upstream element is processed. When this optional parameter for initial value is omitted, the first element of the data sequence is used as the initial value instead. Sometimes we want this initial value to be dynamic and only evaluated at subscription time, not at assembly time. For this, we can use the scanWith operator. The scanWith operator takes a supplier function that returns the initial value. The evaluation of this supplier function is at subscription time. To demonstrate this, we'll provide a supplier that returns the epoch milliseconds. We'll be printing the result modulo 10,000 to make them more readable. Next, we'll separate the flux assembly from its subscription so that we can subscribe to this same flux twice. We'll place a delay of 500 milliseconds between the two subscriptions to differentiate them further. And since thread.sleep throws an exception, we'll need to add the exception to the method signature. Running this, we can see that the results are different and dependent on when the subscription is started. We can also see from the values that they are roughly 500 milliseconds apart, as predicted by the delay of 500 milliseconds. The reduceWith operator works like the scanWith operator. The initial value is now generated at subscription time using the supplier function. Remember that unlike the scan operators, reduce operators return a mono of the final result, not a flux of all the intermediate results. When we run this, we can see again that the results are different and roughly separated by 500 milliseconds. Let's now look at other operators that reduces a data sequence into a single value. For completeness, we'll look at the count operator next. This count operator returns a mono of the number of data elements in the flux. The all operator turns a data sequence into a Boolean value. It compares every element against a predicate and emits true if all the elements satisfy the predicate and a false otherwise. Note that the upstream subscription is cancelled as soon as an element fails to satisfy the predicate. In this case, the value 3 is not smaller than 3 and the subscription is stopped, short-circuiting the evaluation. The any operator works similarly as the all operator, except it returns the value true immediately when its predicate is satisfied. In the any operator, since the first element satisfies the predicate, the upstream subscription is cancelled and the true value is emitted. If no element satisfies the predicate when the data sequence completes, the value false is emitted. The Hess element operator is a special case of the any operator with an equality test. When the element equals the parameter, the operator emits true and cancels the upstream flux. Otherwise, it emits the value false when the data sequence completes. You might assume that given the similarity of the names, the Hess elements operator behaves similarly to the Hess element operator and checks a sequence for more than one value. That would be wrong. Instead, it just checks whether the data stream has any element, and it emits true on any first element and cancels the flux at the same time. It emits false when the flux is empty. Next, let's look at the collect family of operators, starting with collectList. The collectList operator collects a data sequence into a list of the elements. The collectSortedList operator does the same thing in collecting the data elements into a list, but it also sorts it in the natural order. Let's change the source of the flux so that we start with something that's not already sorted and we can see the effect of the sorting. We can change this sorting order by providing a custom comparator to sort the list in other orders. For example, I could use comparator reverse order to reverse the order of the list, or I can provide any comparator function. Another way to sort a data sequence is to use the sort operator. The sort operator works the same way as the collectSortedList, except it does not collect the sorted results in a list. Instead, the elements are emitted individually in sorted order once the upstream flux completes. Similar to collectSortedList, we can also provide a comparator function to alter the way that the sort is done. In this case, let's use comparator comparing math absolute so that we can sort the list by the absolute values. Besides lists, we can also collect the data sequence into other data structures. The collectMultiMap operator collects the data elements into a multi-map data structure, grouped by the key extractor function. So if we want to group the values into odd and even numbers, we could use a key extractor that returns the remainder when divided by 2. We can group them differently by changing the key extractor function. For example, in this case, we are grouping them by their remainder when divided by 3. Let's play around with this a bit more and introduce some negative numbers. We might want to now group them by the absolute remainder. Similar to the collectMultiMap operator, the collectMap operator returns a map data structure with the keys provided by the key extractor. However, since it's a map and not a multi-map, it only retains the value of the last element of each group. More generally, we can use the collect operator to perform many different types of collector operations, including replicating the collectors above using toList, grouping by, toMap, and so on. There's also a toSet option that will help us collect the elements into sets. And there are various methods for getting the sum, the average, the count, as well as various ways of summarizing the data elements. In this example, we are taking the average of the data elements, and we are also taking the average of perhaps the data elements minus 1 and also the absolute value of each data element. From the autocomplete suggestions, we can see that there's a wide range of collectors that can be used out of the box. In this example, in this next part of the example, we use the grouping by collector to emulate the collectMultiMap that we have demonstrated previously. Again, let's group the data elements into a multi-map based on their remainder when divided by 3. To find the maximum value in the sequence, we can also use the max by collector with a comparator that gives us the natural order. Similarly, the mean by collector gives us the minimum value in the data sequence. We can also write our own collector using the Collector.of method. Collector.of method takes 4 functions as parameters and return a collector. These functions are the initializer, the accumulator, the combiner, and the final result calculator. This particular collector returns the average of the square of each element. We've come to the end of this part of the series. If you find this screencast useful, be sure to like and subscribe so that other people can find it too. Thank you for watching. Stay safe, stay healthy, and see you again.